that we notice when we are proving that t is equal to sigma xi is sufficient in the two examples that I have considered, is that we are already guessing what is a sufficient statistics. Now, in many given problems it may not be obvious that what is sufficient, and therefore, this definition of taking conditional distribution to prove that a given statistic is sufficient may be too cumbersome, and moreover it may give rise to, like, we consider conditional distribution of x 1 x 2 x n given say x 1 minus x 2 plus x 3 minus x 4 and so on. It may turn out that this is not free. We may take sigma x I square, it may not be free from theta. Then how to get, or you can say how to guess an sufficient statistic. Fortunately for this, there is a important result called factorization theorem, which readily produces the sufficient statistics. So, this is known as Neyman-Fisher factorization theorem. Named after R. A. Fisher and Georgy Neyman, who proved in around 1939. We are not going to give a very rigorous statement and proof of this theorem, which will be applicable to all situations. Rather, we will consider a discrete case here and to write the proof here. For general rigorous statement and proof, see the book of say Lehman and Romano. We are considering a discrete case here. Let x be a discrete random variable with probability mass function, say f x theta, theta belonging to script theta. Then T x is sufficient if and only if f x theta is equal to g T x theta into h x for all theta. So, we are calling this as the factorization theorem. What I am saying is the distribution can be written as product of two terms g and h, where h is a term where parameter does not appear. In the term g, the parameter theta appears, but appearance of x is through t alone. So, if that is happening, then we say t is sufficient. So, the factorization means that the part of the distribution where the parameter is involved should involve only the sufficient statistics in the form of variables, and the other term should be free from the parameter. Let us look at a proof of this. So, we are considering the discrete case here. So, let us assume say f x theta is equal to g of T x theta h x. Now, let us consider say probability that T x is equal to t, that is equal to, now this is a probability which is involving a function of the random variable x. So, this can be considered as the sum over the probability mass function over those values of x for which T x is equal to t. If I am assuming this factorization, I can write it as g of T x theta into h x x such that T x is equal to t. Now, in the term h x, this T x is equal to t condition is not it is coming, whereas here T x is equal to t will be true for all the values. So, this term can be taken out of the summation sign. This can be written as g t theta sigma h x over x such that T x is equal to t. So, if I consider probability of x is equal to say x prime given T x is equal to t, That means, conditional distribution of x given t, this is equal to 0 if t x prime is not equal to t, and in other case it is equal to probability of x is equal to x prime, t x is equal to t x prime divided by probability of t x is equal to t, which is actually equal to t x prime here, because I am taking t x prime is equal to t. So, if you consider this now, probability of x equal to x prime, t x equal to t x prime, it is same as probability x equal to x prime. So, this becomes equal to, let me consider only this star portion, let me call this as a star here, I will consider this portion. So, this star portion is equal to p theta x is equal to x prime divided by g t theta sigma h x x such that t x is equal to t, that is equal to g t theta h x prime divided by g t theta h x sigma x such that t x is equal to t. Now, this term cancels out. So, you look at this conditional distribution of x given t. Now, this term is free from the parameter, independent of theta. So, the conditional distribution of x given t is independent of the parameter. So, t is sufficient by the definition of the sufficiency. Let us take the converse part of this theorem. Let us assume that t is sufficient for theta. If we assume that t is sufficient for theta, that means I am saying the conditional distribution of x given t x is a function of only x prime and t, that is independent of theta. But this left hand side you can write as p theta x is equal to x prime, t x is equal to t x prime divided by probability t x is equal to t x prime, that is equal to c x prime t if t x prime is equal to t. In other case, of course, it is equal to 0. So, we do not write that case here. This means that probability of x equal to x prime is equal to c x prime t and this term. Now, what is this term? This term will be simply c x prime t g t theta, because I am taking t x prime is equal to t. Now, this is nothing but the factorization, because this term I can write as h x g t theta. So, I have considered this discrete case here, because it is easy to write these conditional probabilities. If the distributions are continuous, then probability of t x equal to t does not make sense, because that will be 0. So, we have to use the conditional density function form. So, the general proof which is given in the Lehmann and Romano, this takes care of all these cases. Another point which I would like to mention here, I have taken theta to be a scalar, but suppose theta is a vector here, then what will be the change here? If we make this assumption, this theta will become vector, this theta will become vector here. Here also theta will become a vector, this will become a vector, this will become a vector. So, there is no change in the argument here. That means, if the factorization holds, t will be sufficient. Let us look at the converse part. In the converse part, we are saying that this is free from theta. So, theta will become vector here and it will not make any difference, and here we will write it as a function of t and theta, where theta is a vector parameter. So, this result holds even if theta is a vector parameter. And another thing is about t also. I am writing here t as a one dimensional term, but that is also not must here. T also can have several components, like it could be t 1, t 2, t k. Similarly, theta can be theta 1, theta 2, theta m. So, let me write this as a remark here. The theorem holds if theta and t are vectors, and another point is that their dimensions need not be the same. Their dimensions need not be same. Now, let us revisit our statement. I said that if t is a function of u, then u is also sufficient. Now, in the factorization theorem, if I substitute t as a function of u, then I will be writing it as something like h of u. If I put that thing, then it will mean that u is also sufficient by the same argument. So, let me add that here. If t is sufficient and t is a function, say alpha of u, then let us look at the density function. F of x theta is equal to g of t x theta into h x. This we can write as g of, now t, it is a function of alpha u So, this we can write as g of a function of u. So, we can just alpha u we can write. So, u is also sufficient by factorization theorem. However, if v is a function of t, then v need not be sufficient. If v is a one-to-one function of t, then v is sufficient. Now, this proof is again simple. If we say v is a one-to-one function, say v is equal to beta of t, then we can say t is equal to beta inverse of v. In that case, g t theta you can write as g of beta inverse v theta. That means, it is a function of v and theta. So, v is also sufficient. Now, the definition of sufficiency can be used to prove whether a given statistic is sufficient or not sufficient, because you can find out the conditional distribution of a given statistic and you can see whether it is free from the parameter or not. However, you should know what statistic you are checking, whereas the factorization theorem yields a sufficient statistic because it is appearing there. Now, if we want to prove that something is not a sufficient statistics, then factorization theorem will not be useful, because to show that it cannot be represented is more difficult than saying that it is a function. So, both of the, that is the original definition as well as the factorization theorem, have different uses. Let me give some examples here. So, let x1, x2, xn follows a normal distribution with mean mu and variance sigma square. I will consider different cases. As I mentioned to you that the sufficiency is a property of the family of distributions, it is not a property of a variable or a property of the parameter, it is a property which is holding for the family. So, here we are saying mu belongs to R, sigma square is positive. Let us take special cases. Suppose I say sigma square is known, say sigma square is equal to 1. That means, I am saying x 1, x 2, x n follows normal mu 1 distribution. Now, let us write down the joint distribution of x 1, x 2, x n. So, that is equal to product 1 by root 2 pi e to the power minus 1 by 2 x I minus mu square, I is equal to 1 to n. So, this if you see 1 by root 2 pi to the power n e to the power minus sigma 1 by 2 x minus mu square. This we can write as 1 by root 2 pi to the power n e to the power minus sigma x I square by 2 e to the power minus n mu square by 2 plus n mu x bar, because here if I take the cross product term, that is twice mu x I with a minus sign. So, 2 will cancel out, minus minus will become plus. So, we get mu sigma x I, that I write as n mu x bar. Now, if you write this function as h of x and this part we consider as a function of x bar and mu, then it is exactly in the form of factorization theorem. We have one term which is free from the parameter and the other term which is dependent upon the parameter depends on the variable only through x bar. So, by factorization theorem, gives x bar as a sufficient statistic. Now, this family is normal distributions with variances known. So, here the sufficient statistics is x bar. In a rough way we can say x bar is sufficient for mu. Let us take the second case. I take mu is known. If mu is known, say mu is equal to mu naught. In that case, the distribution of x 1, x 2, x n is normal mu naught sigma square. So, the joint distribution of x 1, x 2, x n will become 1 by sigma root 2 pi e to the power minus 1 by 2 x I minus mu naught sigma square, that is equal to 1 by root 2 pi to the power n sigma to the power n e to the power minus. Now, this term we write as sigma x I minus mu naught square by twice sigma square. Here you see I cannot separate out x i's like in the case of sigma known case. So, we can say here that sigma x I, this term I write as say h x and remaining term I write as g of sigma x I minus mu naught square and sigma square. So, sigma x I minus mu naught square is sufficient for the family of normal distributions. Now, we may do this factorization in different way also. We may write here 1 by root 2 pi to the power n sigma to the power n, and as before let us expand this. So, we get minus sigma xi square by 2 sigma square plus mu n x bar by, so this mu is mu naught here, sigma square and e to the power minus n mu naught square by sigma twice sigma naught square. If you look at this breakup, then I can consider this as a function of x bar and sigma xi square. So, we can also conclude that x bar and sigma xi square is sufficient, which is of course true here. But if you see this one, this is a larger reduction than this, because here the sufficient statistic is 2 dimensional. Here you have sufficient statistic as 1 dimensional, and of course, you can see here that this itself is a function of sigma xi and sigma xi square, because if I expand this I get sigma xi square plus mu naught square minus 2 mu naught xi. So, this is equal to sigma xi square plus n mu naught square minus 2 mu naught sigma xi. So, this is actually a function of this. So, we will prefer this, because this is a higher level of data reduction, because this is 1 dimensional, this is a 2 dimensional. Let us take the case where both mu and sigma square are unknown. Now, notice here, if both are unknown, then I have to consider the joint distribution by treating both mu and sigma square as the parameter. So, this is a 2 dimensional parameter case here, and the product of the individual distributions of x 1 x 2 x n, it is equal to 1 by 2 sigma square x I minus mu square. You expand this, this is equal to 1 by root 2 pi to the power n sigma to the power n e to the power minus n mu square by 2 sigma square minus sigma x I square by twice sigma square plus n mu, or you can say mu sigma x I by sigma square. So, this term you can see it is a function of, this term is a function of sigma x I square and mu and sigma square, and this term you can call h x. So, we conclude that sigma x I square is sufficient. Here you can see that a further reduction is not possible. However, we can consider it in a slightly different way as follows. We may write this as e to the power minus 1 by twice sigma square sigma x I minus x bar whole square minus n by 2 sigma square x bar minus mu square. That means, I have added and subtracted x bar term here. In that case, this is actually sigma x I minus x bar whole square, this is x bar. So, you can conclude that x bar and s square, where we have used earlier the notation s square for 1 by n minus 1 sigma x I minus x bar whole square, that is the sample variance. So, this is sufficient. Now, you see there is no discrepancy in this statement. If I consider x sigma x I and sigma x I square, then this is 1-to-1 function of x bar and s square, because from here I can obtain this and from here I can obtain this. So, we can say that when both the parameters in a normal distribution are unknown, then the sample mean and the sample variance are sufficient. Now, many times we are using it as a misnomer that x bar is sufficient for mu and s square is sufficient for sigma square. Actually, we have to say this is sufficient for the family normal mu sigma square, mu belonging to R and sigma square greater than 0. I will just explain this discrepancy may occur if we do not maintain this family here. For example, I take another case, say sigma is equal to sigma square is equal to say sigma is equal to mu. Then what happens to the density? It is the distribution is normal mu square. If I have this, then you can look at this breakup here, that joint density, although it is a function of x and mu alone, because sigma has vanished here, this is equal to 1 by root 2 pi to the power n mu to the power n e to the power minus n by 2 minus sigma x I square by twice mu square minus mu sigma x I square by mu square, that is mu. So, here you see this is a function of sigma x I square and mu. Although the parameter is one dimensional, the sufficient statistics is two dimensional. So, although parameter is one dimensional, sigma x I square is sufficient. So, again the statement is again the same, that is sigma x I square is sufficient for this family normal mu square. Of course, we may put mu greater than 0 here. So, sufficiency is a property of the family of distributions. In the next lecture, we will consider few more examples, that is how to apply the factorization theorem to derive the various sufficient statistics, and we will look at the maximal data reduction by means of sufficiency, that is the concept of minimal sufficient statistics. So, in the next lecture we will be considering these concepts.